Recording. Okay. Hi, good morning, guys. Welcome to this webcast. Sharp 11, so time to start. Hopefully you all can hear me. If not, please use the chat window. Any questions, queries as well can be taken up through the chat window. So those who attended my previous webcast, welcome again. If any one of you who is attending now and has missed the previous ones, feel free to reach us. We can share the recordings with you. Today the topic is dynamic and nonlinear behavior. My concentration would be on these two modules. Let's have a look on what this is all about, what the software can do, and what are the things required in the software to be done to do this analysis. Introduce myself. I am Kapil Gaitonde. I am the Territory Technical Manager for Simulation Products based out in Singapore, and I am covering all the South Asian countries, Australia and New Zealand for simulation products. So let's move on. Let me get into the details of this one. So in the past few webcasts we have seen in detail on these different products. Today we are concentrating on simulation, SOLIDWORKS simulation, and to be more specific, we are discussing these two topics, that is nonlinear and dynamic. Okay, so first of all, nonlinear. So here is what it is about. It can be intricate materials like rubber which do not behave in a linear way. It could be materials like plastic, foam, all these materials which show nonlinear behavior when a load is applied. The behavior is not linear in the sense it is not following a linear curve, or it cannot be defined using an Young's modulus, or as well it can be deformations which happen after the yield stress, that is permanent deformations. So if I take the one at the top left here, you can see the kind of deformation that has happened, and it could be a case wherein the part does not come back to its original location. So we want to understand what are the kind of plastic deformations. Those can be understood. We can also get a feel of rubber components like the two animations at the bottom here. One of them is of an O-ring, the other one is of a ring which is going through a plastic component. So we want to see whether it will break, the plastic component will break, whether the rubber component will come back to its original state, how it will move. And the top right one is a kind of a case of a large deformation as well as of a plastic component. So these kind of behaviors cannot be simulated in the modules that we have discussed as of now, which are more of linear simulation. A few other examples. One of them could be this, wherein you can see huge amount of deflection is happening. The spring elements are contacting each other, and what we call a self-contact is happening. We also have cases or more intricate cases like this thing, wherein the material is nitinol. This is an example of a stent being expanded or tested as per the standards. So we can do that in the software, wherein we want to understand the behavior on expansion, compression, bending as well. So those kind of intricate details, detailed analysis using materials like nitinol can be done. It could also be a few more other things like these ones, wherein a stamping kind of operation is happening. A huge amount of deflection is happening on the left bottom here. You can see the level of expansions or compressions that can be simulated on the left top screen here. So all these can be understood using the nonlinear module. And if it has to be seen in terms of accuracy or the level of detail that we can go, this particular video shows it over here. So you can see here, even at the local point with a sharp corner, we are in fact seeing it in detail. So this is what it is. If I put it in the form of text, first of all, in terms of material. So in the nonlinear or the simulation premium module, we can simulate materials like plastic, rubber, foam, which behave in a nonlinear way. It could be large deflections. So comparatively, the deflections are huge, and a linear static module is not good enough for simulating those things. So that can be simulated in the nonlinear module. It could be contact analysis, wherein two parts are coming in contact after a certain amount of time, and we want to see the behavior either during contact or after the contact happens. So all those kind of behaviors can be understood. And finally, material strength variation with temperature change. So it can happen that temperature is changing and the material properties are changing as well. You want to understand and study those as can also be done in this particular module. The second one could be what we are discussing today in the software is the dynamic module. So in nonlinear, we saw more of nonlinear behavior like material properties, etc. When we speak about dynamic, we are speaking about time dependent effects. So this could be one of the examples here, which is of a basketball ring. That is what we are going to see in the software today, wherein it is being subjected to an impulse load either due to the person who is putting the ball or when the ball hits the basketball ring, and we see the response of this particular ring over a period of time. So what you are seeing is actually the response after that initial impulse has happened. So we can simulate these kind of impulse loads or shock loads. It could also be things like this, wherein a bridge is subjected to wind loading. You can get a feel of that. You can understand how it behaves and what is going to happen. So this can be either a harmonic analysis, wherein the wind is coming in a harmonic formation, or it can be also a transient analysis, wherein you have the wind velocity curve and you apply it on the software. If I get into harmonics, it could be something like this, wherein probably an woodcutter example here, which is subjected because of its rotation, it is hitting the entire machinery at a certain frequency, and you want to see whether at a certain frequency it is going to fail or resonate or lead to huge amount of deflections. So this is an interesting example which shows how harmonic analysis can be useful. It could also be random vibrations, response spectrum, or seismic analysis. So typically huge structures subjected to earthquake kind of loading, and you want to see whether it can withstand it. Yes, even that can be simulated here. It could be nonlinear dynamic. Now this is interesting. This is a combination of both, that is the nonlinear behavior which I discussed previously, as well as the dynamic behavior. So this can as well be simulated over here. And if I get into the text, so first of all, if I see in terms of loading, yes, we can apply dynamic loads. It could be as well understanding the stresses on these components either when they are moving or under time varying loads. The loading can be impact or shock loading. Best examples could be shaker test, etc., which are done in the labs. Those can be simulated here. In terms of application, one of the applications that you see here could be of an isolator design. You want to design an isolator which is used for damping the dynamic loads coming in a system. It could be earthquake simulation and a few other details or different applications that can be seen over here. Moving on, the third one could be fatigue analysis. Now we have already discussed fatigue during simulation professional. So in the software I may not go in detail, but in this particular module, as we are getting the capabilities of nonlinear and dynamic, we can as well simulate the life, or we can understand the life of a component which is subjected to dynamic loading, or it could be also random loading. So those best examples of these are the ones that are shown here in the screen, wherein we are a typical shaker test analysis is happening in the lab, and this can be simulated as it is in the software to understand the life of the component. The process remains similar to what we did in fatigue analysis of simulation professional, apart from giving the dynamic loads. And finally, which I may not be discussing today, is more on composites. Simulation Premium has composite analysis as well, wherein we can simulate materials which are of multiple layers, thin composites, layered composites. We can specify the details of each of the layers, the directions, the orthotropic material properties, and do the simulation over here. However, today my concentration would be on nonlinear and dynamic. Let's move on into the software and see how do we simulate it over there. So first I'll take an example of a nonlinear analysis. There is a rubber component here. There is a nice rubber component you can see here, a circular rubber component, and we have a holder or a more of a plastic material component, and this particular rubber component or other way around, the plastic component is going to encompass this particular rubber component, and we are going to see the behavior of it, how the stresses vary over a period of time. In terms of creation of this study, by now you may be comfortable with this front end, especially those who have attended my previous webcast. So if I take the nonlinear option here, we get these options called as static and dynamic. So as we discussed, it can be dynamic nonlinear analysis as well. So in this case, we are looking at only a static nonlinear analysis that can be selected. Okay, and the other details, obviously the first and foremost, as I mentioned before, would be the materials. First of all, one of the components here is plastic. So for that we are specifying the ready-made plastic material. We are taking the material from the ready-made options available here. We are taking the acrylic plastic, and it has all its material details. The second one is rubber, and we need a few more details when we are talking about rubber. Unfortunately, there are less number of standard rubber materials available publicly. Hence, most of them are customized. Other way around, most of the companies have the stress strain curves as per the requirements of rubber components. So those can be input directly in the software, and software calculates something called as constants as per the theory used. One of the theories is hyperelastic Mooney-Revlin, or it can also be, if it is foam, we have Ogden model rather. We can also have hyperelastic Blasco. So depending on the kind of model that we are using, we can appropriately give the material constants. Now in this case, we are using hyperelastic Mooney-Revlin. So typically a stress strain curve that you have can be given to the software. Over here we have the option to give it. These curves can be either in simple tension, planar tension and pure shear, as well as biaxial. By the way, it is not stress strain, but we call it as stretch to stress ratio. So it is a bit different curve. The details can be understood once you go in detail of this particular model. Or other way around, you can as well directly give these constants over here. So those constants can be calculated from the software, or you can manually give it here. In this case, what I am doing, the setup that I am doing, is actually where I am giving the constants directly to this software. So this is how it looks. Two constants have been calculated outside of the software environment, either by the user or he has it. Those have been given here. We are using Mooney-Revlin model, and the two constant model is used. We also have 5 and 6 as well. Okay, so I can do you know? Okay, so as I told you, first thing, as soon as we are creating the nonlinear study, we can apply those materials. While I am here, I would also like to highlight, in this case we are using hyperelastic, but it can be other material models as well, like linear elastic isotropic, that is a default static analysis one. We have orthotropic material model, wherein you can specify the materials in multiple direction. We have nonlinear elastic, so we can simulate elastic behavior of it could be a nonlinear behavior, however it is elastic and the material comes back to its original state. And going into plasticity, that is stresses after permanent deformation or stresses after yielding, we have plasticity von Mises, we have plasticity Tresca, we have plasticity Drugger-Prager. So these three different models are there, wherein we can simulate plasticity behavior. As well, in terms of hyperelastic, we have, as we discussed, these three, and finally we also have viscoelastic and nitinol material models. So based on the material that needs to be simulated, we can select an appropriate material model, and that can be used for simulation. So let me go back here. So first part was defining the material details. Okay. Second is in terms of contacts. So these two parts are coming in contact. So we specify or select those appropriate parts in these particular boxes here, and we say these two are not penetrating each other. So the default one will be bonded. In this case, we are selecting no penetration. That will ensure that these parts do not penetrate each other. So in all assembly analysis, one of the basic things that we need to give to the software or convey to the software is the way the interaction happens between two parts, and that's what is done here. Finally, fixtures, obviously the location where this part is being held. Okay, I would like to highlight, let me get into the right fixture. Yeah, so this is a default fixture wherein the part is being held. You can see here, so the plastic component is held firmly over here, so there is no movement in the plastic component. Whereas in terms of the for the rubber component, we are holding it at a certain location just to ensure rigid body motion does not happen. So at these two edges, you can see these two edges, we have held it in the direction wherein it is not moving. That is, it's difficult to say here, but if I can use this coordinate system here, we are looking at Z and Y directions. So that will ensure the part will not fly off in those two directions. We can as well not use this, but using this will give more stability to the solver. Finally, this is a kind of load here wherein we are actually moving this particular rubber component inside, and if I see here, you can see a value of minus 2.678 inches is given. That is, X is positive here, so it is going inside, and it is moving in a linear way. No curves are given, and we are saying this part is pushed inside this particular plastic component. It takes a bit of time to solve, probably around 20 minutes for this particular setup. I have the results down here. So one of the basic results could be displacements, wherein the part has moved by those 0.2678 inches. So how does it look? Something like this. The animation is a bit fast. So one could be as simple as displacements. I want to see the displacements happening and visualize how it is happening. The second could be stresses. Obviously, stresses are relevant, and we do have an option by which we can see the maximum stresses over this entire setup. So this gives a feel to you how the stresses can this could be the worst case stresses that are coming in the setup. It could also be, you can see the results at different time instance. So one could be what we saw now was for the final. Instead, I can see somewhere halfway through how the stresses. So obviously, when it is coming here, the plastic component is opening up, and we can see some tensile and compressive stresses being developed in this component. Okay, so at different time instance, we can actually see those stresses. We do also have options to probe. So I may be wanting to see the stress variation at this location over a period of time. You can visualize it. Okay, so these could be the different results that one can see. One more useful output could be in terms of reaction forces. So on this point where it is being held, I want to see the reaction force, and moreover over a period of time that can be seen. So when this rubber component is being pushed inside, we are seeing the reaction force variation over a period of time, how it goes, or what is the maximum force required for us to hold this plastic component. So that can be understood using this value. So these are a few different things that can be done in nonlinear. The process remains, as you saw, the front end is same. We just need to ensure we are giving nonlinear material properties, and rest is all in a similar process. Okay, let me quickly show you where this example is in the tutorial. So in case you have the software or you want to try it out, then when you go to help, simulation, tutorials, go to simulation premium, and you'll see this example on nonlinear contact analysis of a pipe holder. Okay, this is the one that I have discussed here. I did not follow all the steps as it is. However, as and when you get an opportunity, you can explore using this lesson. So this is what it is all about. If any questions on the nonlinear module, feel free to use the chat window to ask. I'll take them at the end of the session. You might also see a polling option coming up on your screens that will help you give us any feedbacks, questions, or if you want to discuss this thing in more detail, then you can as well opt to discuss it with one of our experts, and we'll try to get one of our local experts in your region to contact you for further discussions. The second model is on dynamics. Let me show you where is the example on that. So again, I'm going into simulation premium, and I'm taking this example of time history analysis. So this is the example of a basketball hoop. There can be different things. By the way, there is an option over here to open the file directly from here. You can do it as well. However, I believe in most of the companies where the location where the software is installed, the user may not be having read and write permissions. So just give a look at this path. Give a look at this path on your machine, and you can copy the actual path to any local location where you have read and write permissions. That should allow you to do the analysis. Rather, that should allow you to do the analysis and save it. Unlike if you click it from here, it may be only in the read-only mode, and you may not be able to save the results. So moving on, in terms of dynamic analysis, I'm taking this example of basketball hoop. Now, there are a few different things. Now, this same setup, nothing out of the way, alloy steel has been applied. We are holding it at the appropriate location. And if analyzed in a static analysis, I can directly apply a force of 260 lb and we can get the results. So this is not about what we are learning today. You all know how to do this thing. So we are looking at a deflection of around 21 millimeters with a force of 260 lb, and this is applied in the static condition. So it is not a dynamic load. Now let's move on to dynamic analysis. In terms of option, when you create a new study, the last option down here is on linear dynamic, and you can see different options down here. One of them is modal time history. So I would like to highlight, we talk of two different ways in which a dynamic analysis can be done. One of them is using the mode shapes or the modal details, wherein we do the modal analysis first, understand the frequencies, mode shapes, mass participation factor, and thereon those results are further taken. Of course, this is all happening inside the software for calculating the detailed stresses and deflections under dynamic loading. As well, it can be an iterative process or a simple direct sparse process, and what we call as nonlinear dynamic, we can use that method as well. Typically, nonlinear dynamic is a bit more slower and it takes more time to solve. But saying that, obviously it is more accurate than I would not say accurate, but it is more comprehensive than dynamic analysis, modal dynamic analysis. So, but for all practical purposes, people use modal this particular method of modal superimposition, wherein we are doing frequency analysis first. Now, looking at linear dynamic, we have these different options. One of them is modal time history, wherein I have the option to apply the load over a period of time. We have harmonic, wherein we are applying the load in a harmonic way. It could be cases like a motor or a flywheel which has an imbalance and it is applying a certain force continuously at a certain frequency. It could be random vibrations, things like earthquake or the shaker test, etc., wherein it is more of a statistical input that we give to the software. We can do that. And finally, we also have the option of response spectrum. So these are actually many different kind of studies that you can create from here and do further detailed analysis. Today we are sticking to linear dynamic analysis and applying this force using time. So restraint, as we discussed, it is as it is. Material property is nothing different because this is more of a linear dynamic analysis. by the way, in nonlinear we can actually, nonlinear dynamics, we can actually simulate nonlinear material as well. Now coming to force, the way it is applied, typically it is the same, but only the difference is we can actually give a curve over here. So if you observe, the force is varying in this way, wherein from 0 or in the initial time instant, it is like an impulse load. We are applying this particular force of 260 lb force, which remains for a few microseconds, that is precisely 0.4995 seconds, and thereon it is released, that is the force goes off. And just for the sake of giving the curve, it has been given up to 10. If you see it in the form of a graph, it looks like this, wherein there is an impulse and thereon it remains until 0.5 seconds, and it subsides to 0 after that. So this is how it looks. This is how it looks and has been applied. So one part is this, wherein you have the option of applying the curve. Saying that, I would like to highlight, so these curves can come from an Excel sheet. You can as well input many different points here based on whatever you have. In any case, those dynamic inputs can be given to the software. So let me go ahead with this. The second important thing will be damping. Now typically, if there was no damping, then with this particular kind of impulse force, the basketball hoop would vibrate forever. It would never stop. But because of damping, either coming off because of the material or it could be environmental conditions, the part actually stops, and there is a reason for that. Talking about damping, typically it is a bit difficult to know these damping values. It is a different domain itself, and if I take this particular example, we are taking something called as modal damping, and we are giving a ratio of 0.05. So kind of enough damping to dampen the system, but this may not be your true case as well. It is difficult to find the damping values, so you can use the standard values or generic values, but this is what it is all about. Finally, going into the properties, first of all, as I told you, it is doing frequency analysis, so we need to tell the software and how many frequencies to be calculated. The relevance as a user in terms of frequencies is also in terms of understanding the mass participation factor. Frankly, obviously this small training is difficult for me to cover the details on mass participation, but if I tell it in simple words, we need to ensure that enough mass is participating in the direction in which the load is applied, or there are enough frequencies which are captured and in a particular direction, so that we are doing enough capturing of details. Okay, so we can play with the number of frequencies to ensure the mass participation is enough. If I show you the mass participation results, it looks something like this. So for 5 frequencies, we have the values in the X, Y, and Z direction. So you can see in the Y direction, this is at the moment in the tune of 0.5. May not be good enough. We might be required more number of frequencies to capture good accurate results. We suggest anything above 0.8 is good value. Obviously this topic can be discussed in more detail, but unfortunately I cannot do in this quick session. But the process would remain something like this, wherein we understand the natural frequencies. This can as well be done using a different frequency analysis. I believe you all know how to do a frequency analysis, and we can conclude using that analysis on how many number of modes are required for the analysis. Moving on, what remains is few other details in this properties manager here. That is the starting time, obviously 0, ending time, how much time you want to visualize the results after the force has been applied, and the time increment. Obviously the time increment is very important to capture the time steps, and if I put it simply, it can be it can be equal to the highest natural frequency that you have calculated, and that time period can be used here, or even as low as 1/10 of that time period can be used here. Again, this is a big topic to be discussed, not in this session, but yeah, you might want to explore it in more detail. So all these values are not random. They have been given with due consideration and lot of thought. More accurate, slower. Okay, this is done. What else remains? Yes, I think this is what this setup is about. In this case, frankly, it takes more time than what you saw in the previous setup. This could take anywhere around 30 minutes to solve because of the time steps that have been used, etc. And if I show you in terms of results, first of all, displacements, you can see here this is how it looks. I would like to see the maximum displacements probably. If I can use this maximum option, you can do that. Okay, now interesting fact over here, if you observe, when we did simple static analysis, the deflections were in the tune of 21 millimeter. Whereas the same load, when it is applied in an impulse way, that is in a short time period, the time is relevant over here, the deflections are going up to 35 millimeters. So that's the effect of time. The load is same, but the time the time period in which it is applied can make a big difference. Okay, so in terms of results, let me plot this again, and okay, let me show you the probe options. So one of them could be here. You can actually probe the results at appropriate locations here, and I can plot a graph of this over a period of time. You can see how interesting it is. So there was an impulse, the basketball hoop started vibrating. Over a period of time it has dampened. Probably it has hit one more natural frequency at that lower value, and it is again vibrating somewhere around that, and finally it subsides and goes down. Saying that, also from 0 to 0.4 we actually had the force being applied, so that force remained over there for certain time. So with that initial impulse, with that force, these were the vibrations, and thereon once the load is removed, it went down, but it goes on slowly until 0. We also need to remember that this variation is directly proportional to damping, the damping values that we are giving, and those decide how this part is going to vibrate. Yes, same is for stresses. The deflections can be seen. A simple static is done. Anything else that I need to discuss? Let me think on it. Finally, in terms of fatigue, we have done this in Simulation Professional, so I'm not covering in detail, but when you select the fatigue simulation, in the past in Simulation Professional we had only one or two options, that was constant amplitude and variable amplitude. Once you have Simulation Premium, you get these options of harmonic fatigue, so obviously you need to do an harmonic analysis. Those loads can be taken for fatigue analysis. You also have random vibration fatigue. So the way it works is you do an harmonic analysis, and those loads can be actually added over here to do the fatigue analysis. Obviously I don't have an harmonic study here, so I cannot do the analysis. So the steps for fatigue analysis remain same as what we saw in Simulation Professional, so I'm not highlighting much, but that's what it is all about. So this is it for today. I overshot by 5 minutes. I believe that's okay. Let me I believe the polling window should be open. Feel free to give your options in terms of if you want to discuss it in further detail. In the meanwhile, I'm around here for a few more minutes. We can take up questions. Any questions on the topics that we discussed, we can do it today. As well, as I told you, if you want the recording of the previous trainings, please approach us. We can share it with you. On 17th June, that would be our last webcast training in this chain. We'll be doing on plastics. It is on cooling line design and warpage analysis. We'll see how it can be done in the software, and that is what it is all about. So let me scroll through the questions. Those who have questions, please stay back, ask, we can discuss. Those who want to go ahead, thanks a lot for your time. Hopefully it was of use to you. This will be definitely recorded. If anything required, please feel free to contact us. My email address is there here. Kevin's email should also be with you. Okay, let me check the questions panel. Guys, if any questions, please use the Q&A window or the questions panel to ask. I'm around here to take this. Okay. Those written in the Q&A panel on the request for the video, definitely we'll try to make a note of it and share it with you. However, if you miss out, please feel free to contact us. We'll definitely give it. Yeah, one of you wants the slides. Frankly, even though the way I did it was a kind of I took certain slides from my entire presentation. This is a huge presentation which goes on until around 600 MB. So that's okay. We can of course share the video, and if you want anything further details, then definitely we can give you the details. Well, in terms of accuracy, there is a question on accuracy here. I would claim that especially if you are comparing with any other software, for whatever you can do here, I mean the kind of analysis, you will get the same results as that what you are getting in any other software like ANSYS or what is the other software that you have mentioned? I forgot. Okay. As well, saying that obviously the boundary conditions and setups should be same. Saying that, I would also like to say my concentration would be more on my product and how it matches the results with manual calculations or practical tests. We have done enough testing on the software. We do have the typical NAFEMS benchmarks as well as some case studies which have been done to compare the results, and they all look good. As well, this software is there in the market for almost now 20+ years, and the solver has been well tested. It has been implemented in many different industries. I do have a few slides on the accuracy stuff, but I'm not going through today. But of course, if you have any specific questions, please feel free to email us. We'll get you connected to the right guys. Let me scroll through the questions. Thank you. Very helpful. Thank you. Thank you. Good presentations. Okay. I guess could you please email me the video? Thank you for the presentation. Put on the static simulation. How to activate the remaining simulation. Okay. I understand one of them is using SOLIDWORKS Premium. So the modules that we discussed today are more into the simulation part of it. We call them as simulation standard, professional, and premium. So especially what I discussed today is simulation premium module. So all the different analysis that you saw today in the software come after you have these different modules. So it can be if it is simulation professional, then you will appropriately get added. So either you can contact us, we'll get you connected to your local partner to discuss in more detail on what you want to do, and then we can get those modules for you. So obviously these are all different modules coming at a different cost or an add-on cost. Video, this question has been answered. How to access previous recordings? Yeah, previous recordings, again, we'll share it with you. I will not in a blanket way, but if anyone wants them, please contact us and we'll share it with you. Good presentation. Okay. My questions. Is a video PPT or show channel how to access previous recordings. I've been using Strand 7. Okay, there is a question which says I have been using Strand 7 for structural analysis. Is SOLIDWORKS simulation comparable FEA software? Yes, it is a comparable FEA software. Especially typically strand 7 is more beam oriented or for huge structures with thin elements. We can do similar things over here as well. I would say this SOLIDWORKS simulation is more comprehensive. It can do the complete range of analysis as you saw here today. As well, you can also associate it well with the CAD part of it, create drawings once you finish the optimization. So definitely when you compare it with strand 7, you'll find huge number of I would say positive or extra things, and that should that can be seen as a one-point solution for you instead of using multiple softwares. Of course, in terms of accuracy, no worries on that. You should be able to get good things. Okay, one of them is asking me where can we get proper training for simulation premium. So there could be two things. One, of course, if you have the software, you should be getting it from our partners. If any issues, please contact us. We operate in a model wherein we are ensuring we have local simulation experts in your region, so that you get enough technical expertise, hand-holding as well as training. If there is any lag, please let us know. We'll ensure you get the appropriate trainings. Yes, the structure. Sorry, there is a question which says, are the structural analysis tutorials in the help menu? Yes, they are there. Just to reiterate, let me get back down here. So this is the software. This is the software. When you go to help, SOLIDWORKS simulation tutorials. Okay. If it is a comparison with a beam kind of setup, then I can suggest this one. Okay. By the way, I'm going into SOLIDWORKS Premium itself here. Scroll down. Truss structure. You can see one of them could be this one, wherein you will see how to create a beam kind of setup. Okay. So this is one example. We have many such examples which can show you. Our approach is, we have something called as weldments in SOLIDWORKS CAD. Those get translated into beam elements automatically. So you need not waste your time in creating these beam elements and doing nodes, elements, etc. As well, the cross section can come from the 3D. Results can be visualized in 3D. So those idealizations can be done. And yeah, the online tutorial has it. Any other question, guys? Okay, looks like it has stopped. I will give another 2 to 3 minutes. It is 11:43 here. By 11:45 we'll wind it off. Thanks for your time. We'll keep you posted on the videos and further details. Thank you.